Greetings nerds, my name's Ryan. I did my HSC in 2019 and in this video we're going to go through some easy projectile motion questions from actual HSC exams and from NESA practice papers. And when I say easy, I don't necessarily mean that you should find them easy right now. I'm saying within the context of HSC projectile motion questions, these are easy. And they go from 2019 questions all the way back to 2001. Okay, so let's take a look at the first question. An object is projected upwards from the ground and follows a path as represented in the diagram. Which of the following describes the projectile's horizontal and vertical acceleration at the point Y? So horizontal and vertical acceleration at the point Y. So at this point Y. So if you've watched the projectile motion theory video that I did, link in the top right, you'll know that the acceleration at every point in the projectile's motion, including this point Y, is just negative 9.8 in the vertical direction, right? Due to gravity. So this acceleration is just negative 9.8 meters per second squared. So that's the only acceleration that projectiles in HSC physics have. So let's look at the options and see which one best describes that. A, both the horizontal and vertical acceleration are 0. No, that's not true because we do have an acceleration. Both the horizontal and vertical accelerations are 9.8 meters per second squared. No, the vertical direction has an acceleration, but the horizontal direction does not. So that's why this is wrong. C, the horizontal acceleration is 9.8 meters per second squared and the vertical acceleration is 0. Well, this is horizontal. Well, that's not exactly horizontal. This is horizontal. And we know there's no acceleration in the x component. We know there's no acceleration in the horizontal direction. So this is also wrong. So the last option D must be the correct answer. So the horizontal acceleration is 0, that's definitely correct. And the vertical acceleration is 9.8 meters per second squared. I would have said negative 9.8 meters per second squared, but that's the closest to what I would have said. So D is the correct answer here. Okay, next question. Some students were testing the hypothesis that launching a projectile at an angle of 45 degrees will give the maximum horizontal range. Which experimental setup will best test the hypothesis? So the students are testing the hypothesis that if you launch a projectile at an angle of 45 degrees, this projectile, assuming all other factors are equal, this projectile will go further than, say, a projectile with an angle of 30 degrees, or a projectile with an angle, let's make it more clear, with an angle of 70 degrees. So the hypothesis is that this projectile here will go the furthest. It will have the furthest range. So it'll go here. This one will be shorter than that. This one will also be shorter than that. So they're saying that this one will win in terms of how far it goes horizontally. So how would you test that? Well, the dependent variable in this situation is the horizontal range. So the horizontal range is the dependent variable. And the angle which the projectile is launched at is the independent variable. So what does this mean? Well, an independent variable is something that the experimenter varies to see how it affects the dependent variable. And it's in the name, right? The dependent variable is dependent on the independent variable. So just to reiterate, the dependent variable here is the horizontal range of the projectile, and the independent variable here is the angle which it is launched at. Angle launched at, let's say, theta, right? The thing that we would usually call theta. And whenever you're doing a scientific experiment, there is a third category of variables that you need to consider other than dependent and independent, and that is the category of controlled variables. And controlled variables are things that you do not want to change during the experiment. So an example of a controlled variable here would be, say, the planet that you're on. Because if you go to a different planet, the acceleration in the y component would be different, and that could result in a difference in the horizontal range. Another variable that you'd want to keep constant would be the launch speed. So the launch speed of the projectile. The height above ground would be another one that you want to keep controlled. So the only thing that you want to be changing is the angle that is launched. The only thing that you want to change is the variable that you are testing, the independent variable. Because if you're changing other things and the horizontal range is changing, then you don't know whether you can attribute the change in horizontal range to the angle changing or some other variable changing. And so that's why we have the concept of controlled variables. So let's see which one of these experimental setups here fulfills those requirements. Okay, experimental setup A, launch speed. So the launch speed is being varied. So right away, no, because the launch speed is should be a controlled variable, right? We wrote down here, it should be a controlled variable. And we can also look at the launch angle, and the launch angle isn't changing. So you're only testing the 45-degree launch angle. And that, if you're only testing the 45-degree launch angle, then you don't have anything to compare it to, right? So that like completely defeats the purpose of the experiment. So no. And remember, the purpose of the experiment is to test the hypothesis as to whether launching a projectile at an angle of 45 degrees will result in the maximum horizontal range, as opposed to other angles. Okay, so let's look at experiment B. The launch speed is kept constant, so that's good, that's a tick, because the launch speed is a controlled variable. And each one of these is, by the way, like, each one of these would be like test number 1, test number 2, test number 3. Launch angle. Okay, so the launch angle is varying, but it's not varying by much, right? There's 43, 44, 45, 46, 47. There are very small changes in the launch angle. So we'll put a question mark next to this option, and then we'll come back to it later. I'm going to look at D now. Okay, the launch speed is being varied, so straight away no. And the launch angle is being varied, but again, it's with a very small variation between each test. So D is definitely a no. Right, it's a lot of X's. D is definitely a no. Let's look at C. Okay, first of all, the launch speed is kept constant. That's good. That's good because it is supposed to be a controlled variable. So the launch speed being constant is good. The launch angle is the independent variable, which is the thing that needs to be changed, and it is being changed. We're testing 45, and we're testing all these other angles, right? And there's much more of a difference between these other angles and 45 than there is in option B. And so with that, I'm going to say that option C is the answer, and option B is not. Okay, next question. A ball is launched at speed u and angle theta from the horizontal as shown. P is the highest point reached by the ball, so this here is the maximum height of the projectile. Now, I've already done a video on the 3 most common quantitative question types for projectile motion that you'll see in HSC physics. The 3 question types are maximum height, time of flight, and horizontal range. If you'd like to watch that, it's in the top right corner now. So, what is the question actually asking? Ignoring air resistance, what is the speed of the ball at point P? So what is the speed of the ball at point P? Well, we know that at the top of a projectile's motion, so at the maximum height, the velocity in the y component is equal to 0. And this is because when you launch a projectile and it reaches its maximum height, it's changing from moving in the positive y direction to moving in the negative y direction. And so there is a very, very small amount of time where the object is stationary when you consider the y component of its motion. And so that's why we say that v of y at the maximum height is equal to 0. Okay, so v of y is equal to 0 at the point P, right? Does that mean that the speed of the ball of point P is 0? No, it does not, because it's only 0 in the y component. It's not necessarily, or it's not 0 in the x component. So what is the x component? What is v of x here? Actually, let's do that in a different color. What is v of x here? Something that we know about this projectile is that at every point in its motion, the only force that is being applied to it is the force of gravity. And therefore, it's going to have a constant acceleration of negative 9.8 meters per second squared at each point, right? It's going to be the same here, it's going to be the same here, it's going to be the same here, etc. But there is no acceleration in the x component of the projectile's motion because there is no force being applied to the x component of the projectile's motion. And they reiterate that in the question by saying ignoring air resistance, right? So that's another force that's commonly considered when analyzing projectiles, except not in HSC physics. So ignoring air resistance, that means that the only acceleration is in the y component. Okay, well, if the only acceleration is in the y component, that means that a of x, so the acceleration in the x component is 0 meters per second squared. And if the acceleration in the x component of the projectile's motion is 0 meters per second squared, that means that u of x, the initial velocity in the x direction, that means that u of x is equal to v of x, because there's no change in velocity because the acceleration is 0. And so in order to find v of x up here, all we need to do is find the ux. We need to find the initial velocity in the x component. So let's draw an initial velocity triangle, and I'll just make this smaller so there's some more room. So we are launching the projectile with a magnitude of u meters per second at an angle of theta to the horizontal. Angle of theta to the horizontal. Now, if we break this into its constituent x and y components, we get u of x here and uy here. Uy isn't relevant to us at the moment, so I'm going to ignore that, but ux definitely is relevant. The reason this question feels uncomfortable, like I mentioned before, is because usually you're given a value for u, and usually you're given a value for theta. And when I say value, I mean a specific numeric value, a specific number. So this would be something like 30 meters per second. This would be the angle theta would be something like 60. Pretend they are numbers, because it's the same process, but just pretend they are numbers. We're not actually going to be writing numbers, we're going to be writing letters and symbols. So how is ux, the thing we are trying to find, related to theta? Well, it is adjacent to theta. And what can we say that this u is? We can say that this u is the hypotenuse of this triangle. So if we remember our trigonometry, cos of some angle theta is equal to adjacent over hypotenuse. In this case, we have, I'm going to get some more space here. In this case, we have cos of still theta is equal to adjacent, which is ux, the thing we're trying to find, divided by u, which is the hypotenuse of this initial velocity triangle. So if we want ux on its own, we need to multiply the right side by u so that these two u's cancel out. And if we do something to one side of an equation, we have to do it to the other. So we are also going to multiply the left-hand side of the equation, by u as well. So then we are left with ux is equal to u multiplied by cos of theta. All right, so let's recap a little bit. Why did we find ux? Because we know that ux is equal to vx. How do we know that? Because the acceleration in the x component is 0. Why were we looking for Vx in the first place? Because we need to find the velocity of the projectile at the point P, at the maximum height. And we know that the velocity of the projectile at the point P is just going to be equal to Vx because it's got a velocity of 0 in the y component. So all we have to find to answer this question is Vx. And that's basically what we just found, right? So we know that Ux is equal to Vx. So Vx is also equal to u cos theta. So again, let's check the options. We already crossed off the first option. What's the second option? Bu. Is the speed of the ball at point P u? No, definitely not. Let's check D. Is the speed of the ball u sine theta? No. Is the speed of the ball u cos theta? Yes. So C is the answer to this question. Okay, next we have a question from the 2019 HSC paper. A projectile is launched by a cannon as shown. Which arrow represents the velocity of the projectile at its maximum height? So that's similar to the question we just did, right? So we have some We have some projectile being launched here. We're considering the maximum height. We're considering its behavior at the maximum height. We know that the velocity of the y component is equal to 0, but we know that it's going to have some velocity in the x component. So it's going to have some velocity in the x component. And that's similar to what we had in the previous question, right? Well, it's the same as what we had in the previous question. So it's going to have some velocity in the x component at its maximum height. So let's check the options. Is it going to be an arrow straight up? Well, no, that would imply that there exists some positive velocity in the y component like that. And it would also imply that there was no velocity in the x component. So that's definitely wrong. So A is definitely wrong. B is an arrow straight down. That's also wrong because it would imply that there is some negative velocity in the y component at the maximum height point, and we know that's not true. So B is wrong. C is an arrow like that. That would imply that we have a positive v of x, which is correct, but it would also imply that we have a negative vy, so that the resultant force was in that direction here, was in this direction here. And so that's also wrong. So the final answer, D, is correct because it is just a positive velocity to the right, and that's the same as what we said previously. So D is the correct answer. So this next question is from the 2015 HSC paper. A projectile is launched from a cliff top. The dots show the position of the projectile at equal time intervals. All right, so this is like the XY graph here, and each of these dots represents the projectile at T0, T1, T2, T3, etc. All right, so that's what these graphs represent. Assuming negligible air resistance. So when you read that, assuming negligible air resistance, what you should convert that to in your mind is AX equals 0, right? That's what you should convert that into your mind. Which diagram best shows the path of the projectile? All right, this question's pretty intuitive, I'd say. So what does a projectile look like? Well, we know that it looks like a parabola. So if you were to launch a projectile off of a cliff, you'd get something in this kind of, if I could draw good, if I could draw better, it'd look better, but you get something that was the shape of a parabola, right? You'd get something that was the shape of a parabola. So let's look at all these options here. I might just zoom in a little bit. All right, so also we know, something that we know about a parabola is that its gradient is always changing, right? Here you're going to have some gradient. Here the gradient's going to be less steep. Here the gradient is 0. Here the gradient is a little bit negative. Here the gradient's very negative. You're not going to have just if you consider a straight line, right? Say this is x, say this is y. You had some line y equals x, right? The gradient there is constant throughout the entire graph. But on a parabola, the gradient changes. So that's an important point from math that should be considered when doing this question. So the first option here to consider, from the first point to the second point, we have a gradient of a half because the rise is 1 and the run is 2. So our gradient is a half. That's the same thing here. We have a gradient of a half here as well. So there's a straight line between these points. That doesn't happen on a parabola, so we can exclude option A. And if you look at the rest of the points, this is a gradient of negative a half. This is a gradient of, what's that, like negative 1. This is also a gradient of negative 1. This is also a gradient of negative 1. So this part here is entirely a straight line as well, right? So this is not a parabola. This is some kind of funky triangle. So it's not option A because we're looking for a parabola, right? So it's not option A. So option B, we have a gradient of 1 and then a gradient of a half. That's starting to look a little bit better, at least better than option A, because the gradient is becoming less steep the further up the parabola you go. Let's look at the rest of it. So we have now a gradient of negative a half, gradient of negative 1. This is also a gradient of negative 1, right? So this here has a gradient of -1 because the rise is -1 and the run is 1. And so -1 over 1 is equal to -1. So this little bit of line here has a gradient of -1. This also has a gradient of -1 because its rise is -2 and its run is 2. This here also has a gradient of -1. This here also has a gradient of -1. So this entire interval here is a straight line with gradient equal to -1. So we can cross out option B because that ain't no parabola. Okay, option C, and you can kind of tell that if you just looked at them quickly. You can kind of tell intuitively, okay, that doesn't exactly look like a parabola. That looks a little bit weird at the tail end. This looks very, very weird at the start, right? So you can kind of tell it intuitively, but if you wanted to be more thorough, and I'd certainly be doing this in an exam, I'd look at each of the gradients. All right, this has a gradient of 1/2. This also has a gradient of 1/2, crossed out immediately. This has a gradient of 1/2. This has a gradient of 0, which is what we'd expect with a parabola. And with an equal time interval, right? So there's some time here, some time here, some time here. You'd expect the projectile's parabolic path to be symmetrical about the center, right? Where this is like, ooh, this line here is the center. And so we want the parabola to be symmetrical about that center, which is exactly what is seeming to happen here. So we had a gradient of 1/2 here, gradient of a 0 here, gradient of -1/2 here, gradient of something a little less than -1/2, and by less I mean more negative. Now even more negative than the previous one, now even more negative. So D looks to be the right answer because it is in the form of a parabola, which is what we expect projectiles to look like. All right, so the next question is from HSC 2014. A ball is launched horizontally from a cliff with an initial velocity of u meters per second. After 2 seconds, the ball's velocity is in the direction 45 degrees from the horizontal. All right, so let's just draw this out so far. We have a cliff, we have a projectile which is launched from this cliff. So it's launched from this cliff just with a velocity which is in the horizontal direction, And this velocity has a magnitude of u meters per second. And the way that we know it's not launched at some other angle like this, the way that we know that it's launched in line with the horizontal is because it says the ball is launched horizontally. So that's how we know it's a straight line across. So launched horizontally from a cliff with initial velocity u meters per second. So it's going to take a parabolic path like this. And the question is saying after 2 seconds, so after it's traveled for 2 seconds, it's going to be in this position here, let's say. So after it's traveled for, let's get something smaller. After it's traveled for 2 seconds here, it's going to be in this position. And it's saying the ball's velocity is in the direction 45 degrees from the horizontal. So when you first see that, that might sound a little weird because the only time that we've used angles in the context of projectile motion so far has been an angle that looks like this, right? It looks like this. That's not what this is saying. It's not saying that this angle here is 45 degrees. What it is saying is that, and I'm just going to move this t equals 2 up a little bit. What it is saying is that the tangent of the projectile's motion at this point compared with the horizontal at that point, so compared with the horizontal at that point, the angle in between those two lines, so the angle in between those two lines here is going to be equal to 45 degrees. That's what this means. I'll just extend this out a little bit. And so we can form a triangle with that information, right? And I'll just form the triangle like this. And this triangle has some velocity Vx going in this direction, and it has some velocity Vy going in this direction here. Vy. And let's just make this line blue as well. All right. And the actual overall velocity will be represented by this hypotenuse here, right? This vector here. So this is our final velocity, v meters per second. And I'll move this t equals 2 back here. All right, so what is the magnitude of the velocity? What is the magnitude of the velocity in meters per second at the projectile's position when it's like after 2 seconds has passed? So what's the magnitude of the velocity at this point here? So we're trying to find this v, right? We're trying to find this v. We have information about the angle, and we're trying to find this v, so we should probably try and find some information about this v and this v here, okay? So Vx, let's try and find what Vx is. So we know that the only force on this projectile is gravity, which is acting in the y component. And we know there are no forces in the x component. So if there are no forces in the x component, that means there is no acceleration in the x component. So we know that ax is equal to 0 meters per second squared. Now if ax is equal to 0, that means that ux, the initial velocity in the x direction, is equal to Vx, the final velocity in the x direction. So we can say that Vx is equal to ux. Now what is ux? Well, that's the initial velocity in the x direction. Let's look at the initial velocity. We know that because the ball is launched off a cliff horizontally, this line, this vector, I should say, is entirely in the x component, right? There is no initial velocity in the y component. All of the velocity at the projectile's initial launching point is solely in the x component. So we can say that the initial velocity in the x component is equivalent to just u, right? Just u, that's how this vector is notated. So if Vx is equal to ux and ux is equal to u, well, that means that Vx must be equal to u. All right, so Vx is equal to u, and I'll notate it over here. So let's try find Vy as well. Okay, so for Vy, let's immerse this within a Suvat equation. So Sy, Uy, Vy, Ay, and t. So we know that we're considering the projectile at the point t equals 2. We know that the acceleration in the y component is equal to negative 9.8 due to gravity. Vy is the thing we are trying to find, so I'll put a question mark. Uy, the initial velocity in the y component, is equal to 0 because the only velocity that exists at the initial point is in the horizontal direction. Do we know what Sy is? What would Sy be in this case? Well, it would be the displacement. It would be the displacement here. And no, we do not know what that is, so we won't write anything down for that. So let's look at our kinematic equations. We have v squared equals u squared plus 2as. We have v equals u plus at. And we have s equals ut plus half at squared. So we are trying to find an expression for Vy. So we need to have an equation that incorporates v. First equation incorporates v. The second equation incorporates v. The third equation does not, so I'm going to remove the third equation. We have a u. The first equation has a u. The other equation also has a u. We have an a. The first equation uses an a. The second equation also uses an a. And we have a t. The first equation does not have a t. The second equation does have a t. Now the only remaining variable that we haven't ticked in the first equation is s, and we do not have an s, so we need to remove this first equation. So v equals u plus at is the equation that we will be using. I will put a subscript of y at each one here. So vy is the thing that we are solving for. So vy equals uy, which we have as 0, plus negative 9.8 multiplied by t equals 2. So now we have that Vy is equal to, I think that's negative 19.6. Let me check that. Negative 9.8 times 2. Yes, it is negative 19.6. So now we have an expression for Vy. Vy equals negative 19.6 meters per second. All right, and I'll remove all of this. So we should be able to use this information somehow to find an expression for V. So we could try and use trigonometry with the 45-degree angle and let's say the Vy here. So how is the 45 degrees related to the Vy? Well, it's opposite. And what is the V, the thing we're trying to find? Well, that's the hypotenuse of this triangle. So we can say that sine of 45 degrees is equal to opposite, which is Vy, over hypotenuse, which is V. And we're trying to find an expression for V. And if we rearrange this equation, we can multiply both sides by V. These two V's will cancel out and we'll be left with V sine 45 is equal to Vy. And what does this Vy equal to? Well, we know it equals to negative 19.6, so I'll just replace that. And now if we want V on its own, we can divide both sides by sine of 45 degrees. We can divide both sides by sine of 45 degrees. And then this sine 45 will cancel out with this sine 45 and we'll be left with V equals negative 19.6 divided by sine 45 degrees. If you put this in a calculator, you'll find that it is equal to negative 27.72 meters per second. Now let's remember the question was asking what is the magnitude of the velocity of the projectile at t equals 2 seconds. Well, we got the answer V is approximately equal to negative 27.72 meters per second. Now the magnitude of this, right, if we take the absolute value of this, it is 27.72. And if we round that to 3 decimal places, we get 27.7. And that is option D here. Okay, so option D is the correct option. So remember, when it asks for the magnitude, it's just asking for the size, right? It's not asking for the direction. That's what magnitude means in this context. It's just asking for the size. Okay, so on to the next question. HSC 2013. Students performed an investigation. If you'd like to see my videos on HSC Physics projectile motion investigations, click the link in the top right now. That will show you some of the things in this question. It will give you some context as to what we mean when we say investigation in the context of HSC Physics. Okay, students performed an investigation to determine the initial velocity of a projectile. Which row correctly identifies a hazard of this investigation and a related precaution? So a hazard is something that can do damage, can do a lot of damage. And then a precaution is something that prevents the damage from happening. Something that like a precautionary measure is something that you do in order to prevent damage from occurring, in order to prevent the onset of danger, right? So this is a pretty ridiculous question. Hazard, flying projectile, that could be a hazard. So this is correct. Safety precaution, wearing safety glasses, yeah, that could be a precaution, right? You could have like a marble or something, and you could be shooting it, and it might hit someone's eye, so you got to wear safety glasses. That makes sense. Hazard, range of projectile. Is the range of the projectile an actual hazard? No, I don't think so. Let's Just C, safety precaution, measuring the range with a tape measure. No, that's not preventing any damage. That's just measuring something, so no. Hazard, enclosed shoes. Well, I suppose shoes could be a hazard if someone's a real jerk in your class, but usually enclosed shoes would be seen as a precaution if you are dealing with, I don't know, like chemicals or something, corrosive chemicals, something like that. And then let's see the safety precaution, limiting the range of the projectile. Okay, even if enclosed shoes were a hazard, which I don't think it's meant to be, limiting the range of the projectile, unless the projectile is referring to the shoes. You know what? I changed my mind. I'm gonna put this C as a maybe, because the projectile here might be referring to the shoe. No, I'm just kidding. Okay, no, this is obviously a stupid question, so no. Enclosed shoes are probably not a hazard, and limiting the range of the projectile that you're studying is not going to change whether someone throws shoes at your head. Okay, D, hazard, safety glasses. Again, you could use them as a hazard if you're creative enough, but no, not really. Safety precaution, flying projectile, definitely not. Okay, so A is the correct answer to this question. The next question is also from HSC 2013. The diagram shows the path of a cannonball fired from a cannon. Which set of vectors represents the horizontal and vertical components of the cannonball's velocity along the path? Okay, so first of all, we know that there is no acceleration in the x component because the only force that is being applied to this projectile is gravity, and gravity acts only in the y component, right? So there is no force, there is no acceleration in the x component of this projectile. And hence ux, the initial velocity, is equal to vx, is really equal to any velocity in the x component throughout the entirety of the projectile's path. So the velocity here is equal to the velocity here is equal to whatever other velocity in the x direction here. So the velocity in the x direction is constant throughout. The length of the vectors representing the horizontal component of the projectile's motion should be constant at each point in the projectile's path. So this first column here is representing the horizontal component of the velocity, and we want the horizontal component of the velocity to remain constant throughout the entire projectile's path. So the fact that the length of these vectors is changing indicates that this option is saying that the velocity in the x component is changing, so we can rule option A out because we know that the velocity in the x component is constant. This one is also changing, so we can rule option B out. C is not changing, so that's good. And D is also not changing, so that's good. So it's between either C or D. Now similarly, we know that there does exist an acceleration in the y component due to gravity. And that means that the velocity should be changing over time. Specifically, the velocity should be getting more negative over time because the acceleration is in the negative direction. So how do we represent a vector becoming more negative? Well, a positive vector would be pointing up conventionally, and a negative vector would be pointing down. And so if the projectile's velocity is becoming more negative, or at least the projectile's velocity in the y component, if that's becoming more negative over time, you'd expect the vectors to go from something like this, uy, to something like this, vy. And that makes intuitive sense if you look at the graph, because you'd have some velocity going up here, and you'd have some velocity going down here. So let's look at these. Option D just has arrows of constant magnitude pointing down. So that's definitely not right because the velocity has to be changing because we have an acceleration in the y component. And option C looks correct because initially we start with a big positive vertical velocity and then a slightly smaller one, which is where the projectile is starting to curve. And then we have a slightly negative one and then a big negative one. So that makes sense. The correct answer here is C. So the next question is from HSC 2009. A device launches two identical balls simultaneously in a horizontal direction from the same height. Right, so they've been launched at the same time and they've been launched from the same height. Which statement correctly describes what happens? X hits the ground before Y as it is closer to the launch site. So one of the things we know about projectiles is that, at least projectiles in HSC physics, is that the X component of the projectile's motion is independent of the Y component of the projectile's motion. So when you're analyzing the X component of the motion, it has no bearing on the Y component. And so because both of these projectiles are launched horizontally, they both are launched with an initial velocity in the Y component of 0. So if you were to just look at the Y component of these projectiles' paths, you could model it exactly the same by just looking at an object dropped from this height, right? An object dropped from this height with an initial velocity of u meters per second. And that's the same for each of them. So is the time that it takes to fall that height going to change for each of these cases? No, because the Y component of the motion is independent of the X component. So even though this may be launched with either a really big X initial velocity or a really small X initial velocity, it has no bearing on the Y component of the motion. And the Y component of the motion dictates how long it takes before the projectile hits the ground. So X hits the ground before Y, that's false. All right, so A is not the correct answer. Y hits the ground before X, that is again false, because both of these projectiles have an initial velocity in the Y component of 0 meters per second. Option C, X and Y hit the ground simultaneously, that's correct, with the same velocity. They hit the ground with the same velocity Vy, but do they hit the ground with the same velocity Vx? Well, no, the Y projectile is going to have a greater Vx than the X projectile because there's no acceleration in the X component, right? There's no acceleration in the X component because there's no force acting on the projectile in the X component. That means that Ux, the initial velocity X, which we'll get from here, is equal to Vx. And Ux of Y is going to be greater than Ux of X, right? So Ux of Y is greater than Ux of X. And that's just representing the different launch velocities. So the velocity that Y hits the ground with will be greater because of the greater X velocity, and the velocity that the X projectile hits will be smaller. So although they do hit the ground simultaneously, it is not with the same velocity. So answer C, or option C, is ruled out. So that leaves option D, right? X and Y hit the ground simultaneously, which we know is correct, with different velocities, which we also know is correct. So answer D is the correct answer here. The next question is from HSC 2008. An aeroplane is flying horizontally over level ground. It has an altitude of 490 meters. So let's just draw the information that we have so far. So it's flying over level ground. There's some airplane. Oh God, how do I draw an airplane? Oh, looks more like a shark. It'll have to do. No, it won't. I'll redo it. Still gonna look terrible. You know what? All right, there's our airplane, and let's make that level ground a little more level. Okay, there's our airplane, there's our level ground. So, it has an altitude of 490 meters. So let's do it like this. An altitude of 490 meters. And a velocity of 100 meters per second, so an initial velocity of 100 meters per second. as the airplane passes directly above a crossed mark on the ground, so some mark on the ground, right? Some mark on the ground. Actually, I might just make that here. So as the airplane passes over a mark on the ground, an object is released from the airplane. And how far away from the cross will this object land? So Harambe's head is going to travel in a parabolic path as it's released from the airplane. And this is basically just a horizontal range question in disguise, right? And I'm just going to get another copy of his head and another copy of his head and put it here. So this here is the initial position and this here is the final position. And I just realized that's not uy, that is ux. So the initial velocity in the x direction is 100 meters per second. How far away from the cross will this object land? Well, we're trying to find the range here. So what do we know about, what data do we have about the x component? Well, s of x is what we're trying to find. Ux we have as 100 meters per second. Vx is also equal to 100 meters per second because there is an acceleration of 0 in the x direction. And we don't know what t is. So I'll just leave that blank. So let's move this. Consider our kinematic equations, right? V squared equals u squared plus 2as, v equals u plus at, and s equals ut plus half at squared. And what are we trying to find? We're trying to find s. So our first equation has an s. Let's just make that more of an s. Our first equation has an s. Second equation does not have an s, so let's ignore it. And I also just rubbed out a squared there. Our third equation has an s, so that's good. We have a u. First equation has a u, second equation also has a u. Oh, third equation, now the second equation. Vx, we have a Vx, this one has a V, this equation does not have a V, and Ax, both of them have an A. So this one doesn't have a V, so let's rub that out. Thing is, this is all useless, because if we sub in A into this equation, we have, or if we sub in the values into this equation, right, assuming this is all X, 100 squared equals 100 squared plus 2 times 0 times Sx. And that 0 is going to wipe out Sx, which is the thing that we're going to try and find. And now we've just proved that 100 squared is equal to 100 squared, and that's useless. So we don't have enough data from just the x component in order to solve this equation. So let's look at the y component. What do we know about the y component? Sy is equal to, now you might be tempted to write 490 here. That's not quite correct, because Sy is the displacement of the final position from the initial position. So usually we will consider the initial position here as 0, 0, right? We'll usually consider this as the origin. And because Harambe's head is falling down, we will consider this as going negative, right? It's going to have a negative displacement. And so our Sy, and you can actually do this in different ways, but I think the simplest way is to think that the initial position is the origin. So our Sy is actually negative 490. And that's because Harambe's head has fallen 490 meters down. So we're considering the final position relative to the initial position, and we're considering the initial position as being the origin, okay? So Sy is negative 490. Uy is equal to 0 because the only velocity that we have initially is in the x direction. So this is ux, right? This is the velocity ux. I'll just remove that. And I will move this and replace this. All right, so that's our ux. That means there's no velocity in the y direction. So uy is just 0. What about vy? Well, vy is going to be something. We don't know what that is at the moment. We could find it out, but we don't know what it is at the moment. Ay is equal to negative 9.8. And again, we don't know what t is, right? So we'll just leave that blank. So remember, we are trying to find this value here, Sx. And we have this information. So typically what you have to do in these questions when you're trying to find a range, but you don't seem to have enough information to find it, is to first find the flight time. So how will we find the flight time? Well, again, let's consider our kinematic equations. And we're going to be looking at how can we use the data from the y component, s equals ut plus half at squared. How do we use the data from the y component here in order to find t? So we're trying to find t, which the first equation doesn't have, so let's remove that. We have an s. This equation has an s. We also have a u and we have an a, so I'm going to use this equation down here, s equals ut plus half at squared. If this seems a little weird, I have done a video on this, and you can find it in the playlist above. It's entitled Projectile Motion Common Questions, something like that. So you can check it out in that playlist above. Okay. Now let's fill in the data that we have. So we're considering this. I might just rewrite this a little bit neater. We're considering sy equals uyt plus half ayt squared. Sy we have as negative 490. Uy we have as 0. We've got a t there that we're trying to find. And then we have half ay, which is negative 9.8 due to gravity, half negative 9.8 t squared. So because of the 0, this disappears. If we divide both sides by negative, we get, actually, if we divide both sides by -1, we'll get 490 equals half of 9.8, which is the same as 4.9. So we can rewrite this as 4.9 t squared equals 490, just to be a little bit neater. And now if we want t squared on its own, we divide both sides by 4.9. This 4.9 will cancel out with this 4.9. And then 490 divided, I'm too lazy to think about that. 490 divided by 4.9 is equal to 100. And so we have t squared equals 100. Then we have t equals plus or minus the root of 100. Now time can't be negative, so we just ignore that minus, so we just know it's positive. And the square root of 100 is 10, so t equals 10 seconds. So now we have a value for t equals 10. And I'll just remove all this working that we don't need anymore. So t equals 10 seconds. And now we can use that same equation, except now considering the x component, to find Sx, right? So our Sx is what we're trying to find. Ux we have as 100. T we have as 10. I'll put the brackets there as well. Plus half of Ax, which we know is 0, times T, which is 10. The 0 will make everything here disappear. And so we have Sx equals 100 multiplied by 10. Therefore, Sx is equal to 1,000 meters, right? So the range of this projectile from the initial position here to the final position here is 1,000 meters. So we can see that we have the option for 1,000 meters for option B. So option B is the correct answer to this question. So the next question is from HSC 2006. A stone is thrown horizontally from the top of a cliff. So it's thrown horizontally from the top of a cliff with some velocity ux and falls onto the beach below. So it falls onto the beach below. All right, falls onto the beach below. Which acceleration time graph best describes the motion of the stone? So we know that at each point in a projectile's motion, the acceleration due to gravity is going to be constant and pointing downwards. So at each point, it's going to have some constant acceleration, right? At each point in the projectile's path, it's going to have some constant acceleration. And right when it reaches the end, when it hits the ground, that acceleration is going to the magnitude of that acceleration is going to drop very sharply because it's hitting against an object. So that may have clipped, I'm not sure, but it's hitting against an object. So the acceleration is going to drastically reduce. So the option that best corresponds with that description is option B, because we have a constant acceleration for most of the time, and then when it hits the sand on the beach, there's a sudden decrease. So option B is the correct answer. The next question is from HSC 2005. A ball thrown in the air traces a path shown below. So typical parabolic projectile path. Which of the following statements is true? The velocity of the ball keeps changing. The acceleration of the ball keeps changing. The velocity of the ball at the top of its motion is 0. The acceleration of the ball at the top of its motion is 0. Okay, so first of all, like I just said in the previous question, the acceleration at each point in this projectile's motion, right, at every single point, is a constant negative 9.8 meters per second squared. So at each point of the motion, it's got some constant acceleration. So the acceleration is definitely not changing, right? So the acceleration of the ball keeps changing. Let's remove that one. And down here, the acceleration of the ball at the top of its motion is 0 is also wrong because the acceleration will have a magnitude of 9.8 meters per second squared, assuming this is thrown on Earth. So what else do we know? Let's look at option C. The velocity of the ball at the top of its motion is 0. So you might be tempted to select that one, but it's wrong because although the velocity of the ball in the y component at the top of the motion is 0, it still has some velocity in the x component, right? It's still going to have some velocity in the x component. So the overall velocity will still be greater than 0. And so this would be true if the ball was thrown like straight up and straight down, because it has no horizontal velocity throughout the entire thing, and at the maximum height it will have no vertical velocity. But that's not the case with this ball, as we can see from the graph. It is thrown at some angle to the horizontal other than 90, right? So option C is also false, and that leaves option A, the velocity of the ball keeps changing. So that is correct, because the velocity of the ball in the x component doesn't change, but the velocity in the y component does change, right? And so the overall velocity, when you put both of those components together, is going to be changing as well. So that's why option A is the correct answer. The next question is from HSC 2002. The diagram shows the trajectory of a golf ball, standard parabola. Which set of arrows shows the direction of the acceleration of the ball at points P and Q respectively? Well, the only force on this projectile is gravity, and therefore the only force that this projectile experiences is a constant force in the y component of magnitude negative 9.8 meters per second squared. And so both arrows will be pointing down at P and Q. Therefore, option B is correct. And I'll do that in green. Option B is correct. This is wrong because it's pointing up at P, down at Q. That's actually technically correct. It's pointing in this weird direction at C. It's pointing in this weird direction at Q. So C is wrong. D is down like that. and like that, that's definitely wrong. Okay, so B is the correct answer. That was a very quick one. The final question that we have here is from HSC 2001. So an astronaut is standing on Mars. The astronaut throws an object of mass 0.30 kilograms vertically upward at an initial speed of 9 meters per second. It reaches a maximum height of 11 meters. What is the magnitude of the acceleration of the object? When you see a question asking for the magnitude of the acceleration of a projectile and you see 9.8, you might be tempted to go for that one. But we're on Mars, we're not on Earth. This isn't Earth anymore, so D is probably wrong. I'm not going to rule it out, I'm going to prove that it's wrong. So what do we have here? The mass is actually a red herring. We don't need to worry about the mass. The mass is actually irrelevant. And tell me in the comments why. Okay, so an astronaut throws an object vertically upward with an initial speed of 9.0 meters per second. It reaches a maximum height of 11 meters from the launch point. What is the magnitude of the acceleration? So what do we know? We know that this is going to be a little bit difficult to show, but let's say that this is the initial position of the projectile. It shoots up. And this is the final position of the projectile that we're going to consider. So this is initial. This is final. The final position is what was it? 11 meters above the initial position, and it's got an initial velocity in the y component, uy, of 9 meters per second. All right, so filling out our SUVAT table, SY, so the displacement of the final position relative to the initial position is 11 meters. uy is 9 meters per second. Vy is 0 because this is a maximum height question and the velocity of the y component of a projectile at its maximum height is 0. That's a very important point. And then AY is what we are trying to find, which is unusual. And we don't know what T is. So now let's look at our kinematic equations. We have V squared equals U squared plus 2AS. We have V equals U plus AT. We have S equals UT plus half AT squared. And we're considering all of these in the y component of the projectile's motion because the projectile has been thrown just straight vertically upwards. Okay. So we're trying to find AY. This one has AY, this one has AY, this one has AY. They all have an AY. So that's good. And I might as well just leave those ticks there actually. AY, AY, AY. We have an SY. So this one has SY and this one has SY. We have a UY. This one has UY, this one has UY, this one has UY. We've got a VY. This one has VY, this one has VY. The last one does not have VY. It's not looking good for the last one. And T. We don't have a T. The third one has a T, has two T's, which is bad. And the second one also has a T. So we can't use either of them. We have to use the first one. All right, so we're trying to find, again, we're trying to find AY, which is unusual, right? It's rare that we're trying to work backwards to find the acceleration. But alas, we are. Okay, so let's sub in all these values. Vy is 0. Uy is 9. 9.0, but same thing as 9, right? So 2 times AY multiplied by SY, which is 11. So now we have 0 equals 9 squared, which is 81, plus 22 multiplied by AY. If we take the AY to the other side, we have negative 22 AY equals 81. So that's just minusing 22 AY from each side of the equation. And then we're left with AY is equal to 81 divided by negative 22. So 81 divided by 22 is, let's say, 3.68. So we are left with negative 3.68 meters per second squared. And that negative is good because that's just in line with the convention that we are accelerating downwards when we drop something. Whoop, which I literally did. All right, so we got negative 3.68, and it asks us for the magnitude of the acceleration. The magnitude of our AY is equal to the magnitude of negative 3.68, which is equal to just 3.68. These signs are just absolute value signs, by the way, and all an absolute value is whether the number is positive or negative, you just make it positive. So if it's negative, like it is in this case, we just make it positive. And if you write this to one decimal place, right, you get 3.7, and option B is 3.7. So that is the correct answer for this question. All right, so the next video is a similar thing. It's still HSC projectile motion questions, but instead of being an easy difficulty, they're now a medium difficulty. And down here, there is the Module 5 Advanced Mechanics playlist. So good luck, and I'll see you in the next video.